president and founder of U.S. Advanced Computing Infrastructures, Inc., and founder of Chicago Quantum. I'm here to talk today about the D-Wave Inspector. I got to tell you, so first off, D-Wave Systems out of Canada makes a quantum annealing computer. We run on a system called the 2000Q. It's 2048 qubits, and we run jobs, we run projects, we're doing research, and I found the coolest thing ever yesterday. I found the D-Wave Inspector, and I wanted to show it to you. This may be the only video ever on this particular piece of technology, but I think it's great, and it shows you a bit about what tools are available, how you can debug a quantum annealing computer and get the most out of it. And so I've been getting a lot of pushback lately on Facebook and on Reddit and on Twitter that maybe the D-Wave system isn't providing quantum advantage yet. And honestly, who knows? But at least let's arm the people out there with how to get the most out of your D-Wave quantum annealing system. And so just want to show you what you're looking at. So we run a job. 48% of the chains were broken. And in a quantum computer, right, the chains connect the different qubits and the connectors. And so when they break, it doesn't mean it's bad data, but it means some link was broken. And here's a bunch of runs that we did. And so we got 36 matching scores. Those are Chicago Quantum Net scores, by the way, our proprietary stock picking methodology. And this is the best one out of this portfolio, which has 23 stocks. But we're here to talk about the D-Wave Inspector. So in order to get the report, you've already imported your D-Wave sampler. And then you import the D-Wave Inspector. I like to import it as INS for inspector, and then you just do INS show response. D-Wave gives you the data back in response. And then here's your HTTP. It just gives you a link where you can get at the report. And so now we're going to go into a couple of different reports. And so these are inspector reports. The first is just, how to drive. So you can have details about the problem that you're solving, and I can talk through a number of these options. There's details about the solver that you're using. Again, I could talk about a number of those features and options. And then this is awesome. So this is a visualization. So this is the source. So when we plug in the quantum computer, and we plug in the QUBO, or the quadratic unconstrained binary optimization problem, we're really giving it a matrix, and it reads the matrix. And so here's your biases, plus and minus. So anything yellow is a plus bias, anything white is a minus bias. So this is how our QUBO gets loaded, and the solutions, anything that's yellow is a 1, it was chosen, and anything that's white was not chosen. So this is a portfolio response. This particular stock, I'm not sure which one it is, just looking at the chart, but you can see over on the right that where the red is. So this particular stock is connected to other stocks. It wants to be in the portfolio. And each one connects. Each one connects. And so you can see the different connections between the stocks using this. I think that's pretty darn cool. And then you see the bias, the solution, and the chain length. So this particular stock is a chain length of 28. This one has 17. Each one was loaded based on how D-Wave wanted to load it. So let's take a look at the target QPU, quantum processing unit. So in order to map a qubit, you have to map not only the qubit, but the connections between the qubits. And so let's find one that doesn't have a chain length too great, like this one right here. Okay, so there's a qubit. It is connected to it looks like one other qubit, just a few, maybe a couple. And then you keep looking through and you see all the qubits that have these enormous sets of connections. And so these are all the warnings that you get. Chain length warning, chain length greater than 7. And here's your target. So you can see each one runs through. Now, if we were more in the engineering mindset, we might manually chain up those qubits, but we can't now. So why does it connect them like that? So let's go back to the first page. So this is our target QPU with all the warnings. What's interesting is here's the energy landscape as it did the samples. And so for us, the best energy is a negative energy. It is the most negative. So there's some pretty good answers here at -5. And then here, there's actually two answers at right around the same energy. And then you see some of them are positive. They're just really bad answers. So you can see on the left where the different qubits are activated, the color changes. So we don't really engineer down to that level of precision, but here's what we do use. We use details about the solver. So in this case, we're using a D-Wave 2000Q solver number 6. It's got 2048 qubits, which is great. It's a lower noise system. So it actually provides better outcomes. And in this case, you can do an annealing range of 1 to 2,000 microseconds. So let's talk about it. This particular one, it's set as a default at 20 microseconds. Thermalization of 1,000. You can set up different scheduling of annealings. We don't do that, but you could have it stop and start. You can also do reads up to 10,000. So think of it as a deck of cards or a pair of dice, and you can roll the dice or deal the cards one time and see what this cubo gives you, or do it 10,000 times, and then it gives you all the answers. In some cases, it gives you a histogram where it groups all these similar questions or similar answers together. Others, it's raw, and you can see really how it's running. Now, the H range and the J range are the range of your linear terms and your quadratic terms. So in this case, it doesn't mind a linear term. So linear term is the actual value. So in our case, a linear term is expected return. I have a stock, PayPal, I expected to earn 12%. So in theory, we could put 12% right on the qubit, but it only takes -2 to 2. And so it's not great. How am I going to put 12% on there? I could put 0.12. Let's take a look. On the J range, those are your connections in between the qubits, your connectors. So this, in our case, would be the covariance between the two stocks. So covariance between, let's say, stock 1 and stock 59. And so if I look here, you see all those different connections just to get things to talk to each other. And so we take a look, and now those have to be between 1 and -1, which kind of makes sense. It's covariance. But you can extend the range. So if you allow D-Wave, you can H-gain linear terms. You could say, look, handle from 5 to -5. And for my covariance, handle from -2 to 1. Okay, good to know. Now let's look at the problem we sent it. So in this case, there's this thing called post-processing. We'll probably see another one that has it. It could be either optimization, sampling, or off. For us, it would always be optimization because we're doing an optimization problem. In other cases, people are just trying to pick good random samples, so they might do sampling. This does a little bit of improvement by going back and making sure that it's got the exact best energy values. We've seen only tiny, tiny improvement using it, so sometimes we use it, sometimes we don't. We have 60 variables because we're doing 60 stocks. That's important. So when you read our articles and it says 60 stocks, it means 60 variables. What that means is those 60 variables are mapped to 1,242 qubits variables. So this is what 1,242 qubits looks like on the D-Wave. The maximum chain length is 31. So that means for each qubit that has to talk to another qubit, sometimes they have to link through 31 qubits. Chain strength is 1, that's a setting, and if a chain break happens, it uses majority vote to find the value. So you don't have to throw away the value. Post-processing overhead time, if we were to use it, is 593 microseconds. The programming time just to get the qubits on is 11,012 microseconds, and the qubit access time in total, it's a lot. It's 170,000 microseconds. So just good to know. So the annealing schedule, we set it to 100 microseconds, not the default of 20. And that means the annealing schedule starts at 00 and ends at 100 comma 1. And we don't reinitialize the states. That's used if you're doing reverse annealing. So it teaches you a lot about the problem, teaches you a lot about the solver. And what's important, for me, really important, is to understand that you have chains that can be quite long with a chain strength of 1. So let me go back. Chain strength equals 1 means D-Wave is not minimizing chain length. So in this case, it's 31. So this is if this was a live audience, I would ask for questions. So instead, I'm just going to quickly run through, right? These are the 60 console warnings about long chain lengths. It's important for you when you look over to the right-hand side to see that I've got biases that are white, that are minus. So if it's an icing problem, I'm loading it with -1, +1. If I'm doing a binary solution, I've got +1, -1. We load in a binary solution. It's possible D-Wave converts it to an icing, but either way, you see the plus ones are blue, dark blue, and you see the minus ones are white. And what's interesting is in order for these two particular qubits to talk to each other, to communicate, they have to go through very, very many steps. So let's take a look at a different problem. So now I want to show you something. This is very important. You see this particular cubo loaded left. It looks like left to the middle of the right. This cubo loads lower right to upper left. So it's very different. By the way, same size problem. It's 60 qubits. Okay, we're going to do 500 rolls of the dice. But this time it's only a max chain length of 23. So this particular loading of the problem runs better. It's cleaner. Same amount of QPU access time, but you can see here it's just lower chain length. So it's a less dangerous kind of loading of the system. We also have 0 or no post-processing. Again, about the solver, nothing changed. Your ranges are the same. It's the lower noise, 2000Q. But what I want to point out here is take a look at that shape. And if we were to look at the force directed, this is where you see the solution. And so the solution connects these different qubits. So anything that's yellow was chosen, which is great. And now you see the energies that were pulled out are more concentrated. So I say more concentrated because they're loaded much closer to the ones that we want. Okay, they're closer to the look at that, minus 8.8. That's an amazing energy source, right? Energy value. And you see two of them at -7. So we are just getting a terrific, terrific loading here. So I wish I could remember which one it was, right? And I would do it all the time, but I didn't do much. I kept the chain strength at 1. It just happens to be a nice loading of the problem. So this one's going to give us lots of good answers. Let's take a look at this one. It's another problem. Again, good values, but you see here the energy is -6. The other one was -8. I'm going to show you again. I ran this problem. I get values of -8.779. It's 8.8. Wow. That's a stock portfolio that I want to pick because Chicago Quantum Net Score likes highly negative values. I come over to this next one, and these were from our experimental runs last night. Well, this one's only 6.7. I'm sorry, -6.2. You also see how much we're loading here. We're all over the board. If you look at the other page, here's the solution. So not a lot of stocks got picked. Maybe it was a smaller portfolio. So let's take a look at the problem. Post-processing was off, 60 variables, 32 chain length. This time, we reduced the chain strength from 1 to 0.2. I've only ever gone to zero point 0.1. I don't dare to go with lower chain strength. So the chain length went up, and this time I'm using 200 microseconds of time. So what I learned in our simulated annealer is if you want deeper, better solutions, and you see we didn't get them here. But if you do, a lot of times you have to give it more time. And by giving it more time in the early stages of the annealing process, it jumps a lot more. It tunnels. It looks. It says, okay, I could be here, I could be there, I could look at all different values. Before it starts to, as the environment gets cooler, before it starts to harden, think of it like jello. It hardens into a shape. It doesn't say it can't move a little, but it hardens. And so, um, I'm sorry, that was my number of reads at 200. The annealing time here is 20. It's the same point though. If the annealing time was 200 microseconds, which I have used, it gives it a lot of time to look for answers to problems before it settles. This one at 20 microseconds, it's pretty quick. That jello is setting fast. So go find me a good answer and go hit it. And on this type of an environment, you're not going to find very good answers. Let's take a look at another problem. Wow, look at that energy. Negative 10.12. And really nothing bad. Negative 7.5. This is a terrific solution. And if I look, you see a lot of connectivity, a lot of stocks were picked. So let's take a look. If I look at the QPU, I see it's loaded left to right, plenty of white space around the edges. It still has 60 warnings. Some of those chain lengths are pretty crazy, right? Those connections. And you can actually see which qubit is connected to which qubit. So there are people that really care about a specific qubit. There's certain types of work you can do, right? We don't do that. We're finance guys. And so, wow, what a great answer. So let's take a look. What kind of problem did we feed it here? So post-processing still off, still the 60 variables, 30 max chain length. We set the chain strength to 1. This time we ran 500 reads. So we let it have 500 rolls of the dice, and the annealing time was 100. 100 is pretty high for us. It's 5 times the default of 20. And so we let this one have lots of time to settle in and look for answers. And you can see here with an energy level of minus 10, we got lots of answers. So we felt good about that one. This one, it's upper left to lower right. Again, plenty of white space. You'd kind of hope that D-Wave would be looking. So this one, great energy value, minus 9.7. But some bad ones. So this one, for some reason, this Cubo is giving us just some crazy spread of answers. Oh man. So what do we get? We get different answers here. Could take a look at the linear force. So this says what are my qubits connected to? I don't really know how to use this one, but sure is pretty to look at. Right? These are my biases for specific qubits, for specific stocks. Let's look at it that way. These are my stocks loaded, and this is who they connect to. So as long as the system isn't broken and we don't have bad qubits, my stocks connect pretty well. And you can see how I compare different stocks to different other stocks. So that's interesting. Let's look at this problem. Optimization turned on. So what this does is it has D-Wave do post-processing on optimization to go make sure I got the best values possible. I have a chain strength of 2. Now what that does is for problems where I'm worried about broken chains, this brought my maximum chain length to 24. That's great. Okay. What's interesting is a chain strength of 2, and I couple it with an annealing time of 40. So now I have fewer chain breaks. I have stronger chains. I'm giving it 40 microseconds to look for an answer. I'm doing 500 rolls of the dice, and it did 140,000 microseconds. So kind of interesting. It's actually less time. I think maybe because it's holding some of that time for post-processing. I get good answers. You can see how the problem was loaded. I still have 60 warnings. My guess is that those warnings just stop at 60. But you can see that, well, just take a look. The connections are simpler. It's not like a subway map. It's much more like a rectangle, simple rectangles. So by doing a chain strength of 2, I have much simpler connectivity between the qubits. And then finally, here's the first one that I have here. You can see fewer plus 1 or solution bias answers. Take a look at the tightness of that energy. Now, it's a minus 6.8. So all these energy levels mean the same thing. So they are an actual value. Minus 6.8, not that great. But look at how tight the answers are. So for whatever reason, this Cubo is doing a really nice job of finding the answers. You can see it's left coming to the right. Let's take a look at how we set up the problem. Chain strength 0.2. So what that means is that we said, look, we're not so worried about the chain strength. We want you to relax your constraints. Relax. So chain strength is 0.2. We want you to take 200 reads. We don't want to waste too much money here. You can see the QPU access time is only about 60,000 versus 140 or 170,000. Still 60 variables. My chain length is only 28. So for some reason, I'm not getting a lot of chain length. I said anneal for 20 microseconds. So give me a quick look. Just give me a quick look. What do you get? And what you get is you get some pretty good tight values. So I'm getting a pretty good read on these answers. So let me just do a quick review on what we learned. So the first thing is D-Wave's pretty awesome, and they give you all these tools to manage the environment, to manage each particular QUBO that you send and how it's going to interpret it. And you understand your ranges now, so you know kind of your variables you can play with. You also know that for certain types of problems, right, you could do post-processing, you could affect the number of variables, you could affect the chain length, chain strength, the time or the money that you spent, the number of reads, your answer mode and histogram so that you see the answers arranged by energy level in order, and it consolidates up duplicate reads. You can set your annealing time. We today do not have annealing offsets, but we understand that we could actually set each of the qubits and give it a bias. By the way, one of the things we do is we let D-Wave correct for bias issues or bias drift. So we do that automatically. All right, so just as a public service announcement, I'm going to take you to our website. So it's chicagoquantum.com. ChicagoQuantum.com is a company owned by U.S. Advanced Computing Infrastructures, Inc. We create quantum advantage. We sure try. Here's our team. The three main players of the team. You got Clark Alexander, PhD in math, Alex Kahn, senior executive in IT, insurance, and optimization and master's degrees, and he studied quantum computing as a certificate. And this is myself, Jeff Cohen, senior executive. We also have associate team members Marwan Salhi, PhD in theoretical physics, and Terrell Franz, who's more on the finance side, but is leading the quantum education process at Harrisburg University. Harrisburg University has Quantum Palooza, which has been a really, really successful way to get people together. We love that. And here's Alex giving a pitch to students at Duke University to teach them how to be consultants. So, and then we published stock portfolios. And our ideal portfolio, which is picked with both quantum and classical processes, outperformed the benchmarks in the first measurement period. We actually show that data in a Medium article. And we did a Twitter feed, and that's how we know that we should publish a stock portfolio. We tweet under the name at Chicago_quantum. And honestly, we're learning a ton. And we're just so blessed and thankful we've been on TV. The Quantum Hermit talked about us, Swiss Quantum Hub, Ideas, NASA and the SAO Astrophysics Data System retweeted our or reposted our article. Instant Quantum Technology, Reddit, Quantum Finance Blog, Quantum Palooza. We're really all over the place, and we do post our answers to ResearchGate, and so our published research and our formal research. But what I want to show you is if you click through, so we try to keep everything really simple. So if you click through to our Medium article, oh look, I have 2 free stories left this month. That's terrific. So let's take a look. So we updated it August 3rd with answers. So what were the answers? Just jump right to it. So we had a Chicago Quantum Net Score portfolio. We had a Chicago Quantum Ratio portfolio. By the way, spoiler alert, we have a genetic algorithm portfolio, and our universe is 60 stocks. It could be any 60 stocks. We do US highly liquid, and we're just doing them alphabetically, just for research purposes. These 2 stocks were picked by our genetic algorithm. They were also picked in every single Chicago Quantum Net Score Great portfolio. Here's what happened. Boom. Booyah. Jump right up there, let you see it. You're going to be amazed. The ideal stock portfolio, 2 stocks, returned 12.2% in the period. By the way, we do not invest in our own portfolios at this point, so everything we're doing is research. The all stock 60 portfolio returned about 3%, which did the CQNS, CQR, and the S&P 500. So I would say the difference between 3.08 and 2.7 and 3.17, they're all about the same. But those 2 ideal stocks that just popped, those are our all-stars, making a ton of money. So our very optimistic interpretation of the results, we found the goose that lays golden eggs, and you better go pick up those eggs. The other interpretation is that when we generalize the solution, when we make it more consumable for the investing population, we see good solutions that reflect the population it was drawn from. Is it the best? Maybe not. It's good. The realistic interpretation is that 3 weeks of results, it's not enough to draw a conclusion. We might have gotten lucky. But that's okay. Sometimes I'd rather be lucky than smart. In this case, at least we see good general performance with the benchmarks of our particular 2 portfolios, and our ideal stock portfolio just blew the benchmarks out of the water. Please take a look at our Medium articles. Please check it out. We're Chicago Quantum on all these different Medium. So this is Jeffrey Cohen. Thank you very much for listening. I appreciate your time and attention. You take care. Be safe.